Good day. Welcome everyone to our webinar presentation. My name is Adam Harris, Managing Director for C-Therm Technologies. Very pleased to welcome you to today's webinar presentation. This is one of our feature applications webinars where about once a month we feature an interesting novel application where thermal conductivity and the related thermal characterization of such materials is of interest. To start 2020, we thought we'd start with biomaterials, and the reason is over the course of the last year, we've seen a significant increase of interest in characterizing such materials. A lot more work coming through our lab, looking at assistance in characterizing these materials. And so we thought this is a newer application area, would be one to start the year with in terms of featuring a little bit of information on how the characterization is done, why the thermal properties are of interest, how do we define performance of these candidate materials. So a good place for us to start in 2020. This presentation, we haven't timed it exactly, but it should run about 45 to 55 minutes. We will reserve an opportunity for a Q&A session at the end of the presentation. I will take us through a little bit of background material on C-Therm as a company and talk a little bit about the underlying technology that's being applied in the thermal characterization. And then I'm really pleased to introduce my colleague, Dr. Michael Landry, who's been really doing the heavy lifting in terms of working with clients, assisting them in the characterization of these types of materials. And we'll talk a little bit about some of that experience that he's helped with. So without further ado, I think we'll get started. Just a reminder that the telephone lines are muted. We do that, again, to preserve the audio quality of the recording. This webinar will be posted on our website. So if any of your colleagues weren't able to join us due to scheduling conflicts, there is certainly an opportunity to review this material again in the future. As we go through the presentation, if you want to flag any points, commentary or questions, please use the chat box feature. It's a great way for us to capture that feedback and questions. If I'm not able to address them in real time, we will make a point of reviewing them in the Q&A session at the end of the presentation. All right, so let's get started here. First off, a little bit of insight, I guess, about C-Therm Technologies. In looking at the roster online, I see a lot of familiar faces, folks that we've known for several years. But I also see some newer faces and names that, we may not be as familiar with us, and we're not necessarily as familiar with you. So I wanted to give a little bit of perspective on what C-Therm is, or who we are as an organization. And really, we're really niche specialists when it comes to thermal analysis. So we don't offer a really super broad range of products. We're very focused on the area of heat transfer and specifically looking at thermal conductivity and some of those related thermal characteristics of materials. Our vision and goal, raison d'etre in life, is to simplify thermal conductivity. And that means making it easier to operate and also making it easier to obtain truly representative application data under an increasingly more dynamic range of environments and applications. We would support a lot of work in the nuclear fields, in energetics. We have a really specialty line of high pressure cells. But at our core, we've got three main products which support the characterization of such heat transfer properties. At one end of the spectrum is our entry-level option, the TC kit. This is really designed for researchers on a tight budget. It provides a very basic capability for characterizing the conductivity of solid materials, oriented really to kind of undergraduate researchers, sometimes incorporated in course lab work and teaching heat transfer courses, but also, certainly a basic capability in characterizing materials, lower conductivity solid materials, and a great starting point if you're just getting into conductivity. Our research-grade instrument is called Trident, the Trident thermal conductivity instrument. It offers a range of different sensor options. We'll be really featuring the MTPS sensor option, and I'll describe this in a little bit more detail here shortly, but you'll see that certainly highlighted in some of Dr. Landry's work. And then we have another product called the TX Touch Experience platform, which is for measuring the thermal effusivity of materials, mostly textiles and fabrics, but Dr. Landry will reference a little bit of some of the interesting work on effusivity and why it's potentially of interest in biomaterials from a sense of touch. But that gives you a basic overview of our product line, and it's really centered, our capabilities centered around the measurement of heat transfer properties, specifically thermal conductivity and thermal effusivity. So to just dive in a little bit more there on the middle one, Trident, where that's the instrument that's being featured in today's presentation. This is a newer product. This was launched last year to great fanfare as now our top seller. Really powerful instrument. Really oriented towards the research grade market. And it brings together the three most prominent transient methods for thermal conductivity. These are all contact-based measurements, and they're very complementary one to another. I'll describe a little bit of some of those differences amongst them, but we have the Flex Transient Plane Source, sometimes called TPS, or a hot disk style sensor. We have the needle transient line source sensor in this platform. This is sheathed in stainless steel, very, very robust. And we have the MTPS, Modified Transient Plane Source. This is a single-sided sensor. It's sealed, so it's perfect for testing liquids as well as solids, powders, pastes. It's our most versatile and easiest to use sensor, offering the best sensitivity and precision. So I'll describe a little bit further how these different techniques complement one another, but the point we try to really communicate and educate the market on is that when it comes to thermal conductivity, there really is no silver bullet. There is no one technique that does a good job of handling all the scenarios in terms of sample formats or environmental conditions under which you want to test. And so when it comes to conductivity, what we've certainly determined over the past 20 years is that it's much better to have options. And so that's the tag to Trident. It's one instrument with three methods for thermal conductivity. Ultimately, University. He certainly has some really interesting ideas on organization behavior, motivations, hierarchy of needs. But this quote to me really resonates here that we are often guilty of a bias when we're used to the solution that we've always applied. We sometimes try to shoehorn it into situations that doesn't necessarily fit. And I think he sums it up nicely, writing, when all you have is a hammer, everything looks like a nail. And that's something that really fits with our approach with Trident. So the needle probe is really oriented towards those very sticky situations. If you're dealing with a polymer melt, for example, something that might bond to these other sensors, then that's a situation where you're much better off having this kind of robust needle. It's not quite as sensitive and accurate because of that stainless steel sheathing that goes around with it, but you gain a lot of robustness in that. And there's a lot of situations where that's a significant advantage. With the TPS method, it's available in a range of different size sensors, which gives you some different options depending on the dynamic that you're dealing with. It's really oriented towards a more experienced user. It gives the user control over the experimental parameters in terms of the test time, the power applied in the measurement, and gives you a lot more finer control over that experiment. The flip side of that is that you have to be a bit more experienced in operating it. So our simplest and easiest, most versatile sensor is the MTPS. It also offers the advantage that it's a single-sided sensor. So in this one, all you do is you place the sample on top of the sensor. With the TPS, you'll sandwich this sensor in between two homogeneous samples. So some different sampling requirements as well. This active area for the MTPS sensor is 18 millimeters in diameter, so that's the minimum sample requirement for working with the MTPS method. I'll detail a little bit more the theory of operation to MTPS in the next couple of slides, just where that is going to be specifically referenced in Dr. Landry's work. But this gives you the high-level specifications for these different methods. You'll notice some different temperature ranges, the precision statements, the accuracy, and some of the different industry and ISO method, ASTM and ISO methods associated with these techniques. So that gives you a good overview of the capabilities there. So this is a picture of what an MTPS sensor looks like. So to detail a little further, the active area is that green area in there. The red is a room temperature vulcanized silicone that forms a liquid seal on the sensor. That makes it very appropriate for testing liquids, gels, semi-solids, powders, etc., as well as, of course, solid material. The most important part of the sensor is that chipset that is sealed in the housing there with the RTV. It's comprised of an alumina substrate, and there are two circuits to the sensor. There's the central coil, which is the active sensor, and then there's what we call the guard ring around the contour of the sensor. Both of those circuits are electrically heated, and this is how the measurement functions. The reason for the guard ring is to ensure that we get a one-dimensional heat flow into the sample material. So heat travels in the path of least resistance. We've got an insulative backing material on the other side of the sensor chipset. Both the coil and the guard ring are electrically heated, and this ensures that the measurement sensor, which is the main coil, has a unidirectional pathway into the sample material. So that coil in the middle is both a heater and a detector. We're monitoring the voltage drop on that coil as it's inversely related to the temperature change over time. So it's a calibrated method. We calibrate that voltage drop change to temperature change. And the relationship of that temperature change to the effective thermal conductivity of the material is an inverse relationship. So if we have a really steep rise in a temperature change, we have a really low thermal conductivity material like a foam or insulation. If we have a more negligible rise in temperature change over time, we have a good heat sink material on the sensor, a metal material, a high thermal conductivity, good heat dissipator in contact with the sensor. A little bit of nuance and context here. So the measurement times are kept by design to be intentionally short. So a typical test time is in the range of 1 second. This is a very quick measurement. If you exaggerated those test times, certainly you would start to lose heat laterally in the sample, but because this is a very short duration pulse, that guard ring is proven to be very effective within that time scale. And that also has a number of benefits in the types of geometries and samples you can handle. It's very important, for example, in testing lower viscosity fluids where convection may be a greater concern. The longer your test time, the more opportunity there is for convection. So it's really important in some scenarios to keep that test time short. Short test time also means you can test thinner types of materials as well. You want to make sure that measurement pulse stays within the boundary conditions of the samples for the duration of the measurement. So typically that requires a sample that's about 1 millimeter in thickness, and as the material would have a higher thermal conductivity, that minimum thickness increase would increase. So the higher the conductivity, the thicker the minimum thickness requirements. If you're dealing with thin films or other materials that might be thinner, there are other options. For example, the TPS sensor has a slab method, which is really good for metal sheets. We have another sensor which offers, good characterization capabilities on thin films. So there are different options available depending on the types of situations that you're dealing with. But I think this provides a good general overview on the method. The one last point I'll just leave you with is that you don't have to interpret any of those voltage time plots with the MTPS method. So there's no regression analysis here required by the user. The beauty of the MTPS method is it's really, essentially point and click, and you get the thermal conductivity results. So this is a screen capture from the data. It's hard to make this out, but we've got the thermal conductivity data plotted. You'll see a tabular summary of the thermal conductivity, the thermal effusivity as well, and the temperature data all recorded in real time with the software. So it makes for a real nice solution in terms of measuring conductivity. Okay, so that's a good bit of background. I've got a short little video to play for you that just summarizes some of this information and provides a little bit further information. And then we're going to transition to Dr. Michael Landry's section on characterizing biomaterials. Just before I hit play on this, if you don't have your computer speakers turned on, this is one portion of the audio that does come through and transmit through the online portion. So I would just encourage you to turn your speakers on for a second.
Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle Method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all three methods: intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Okay, it's a nice video. It does a really good job of, I think, demonstrating how the equipment operates, and at the very end you get even a few shots of that, some of the high pressure cells in our product line. So we thought that might be interesting to a few folks online. All right, look, without further ado, I want to introduce a colleague of mine, Dr. Michael Landry. Dr. Landry joined us last year, is doing great work with our group. He worked at the Montreal Neurological Institute while doing his PhD at McGill University, one of Canada's top universities. He worked on biomaterials, polymer, and Parkinson's drug candidates for eternal stimulation drug delivery. His focus lies on polymer materials for biological systems and designing natural polymers for interfacing with biological systems. So let me pass over the baton here to Michael, and he'll take it from here.
Thanks, Adam. Thank you for that awesome intro. So today I'm going to be talking to you a bit about some of the thermal conductivity and related properties of biomaterials, and specifically how we can measure some of these properties and some of the tools that we can offer researchers in this area. To first start, I'm just going to explain specifically what actually is a biomaterial. A lot of the audience here probably knows what these are, but just for people that are potentially just foraying into this, biomaterials are those materials, be it natural, synthetic, alive, or lifeless, which are made of usually multiple components, such as composites, that interact with biological systems. Around us, day by day, we have these biological implants that are being put into us, be it stents for opening up arteries and veins, artificial, in the case of artificial veins, we have the polymer type materials. In the case of tissue engineering, we have the advent of these 3D printed polymer matrices. But biological materials are also relevant for treating burns, in the case of burn treatment pads. So they're all around us every day, and it's very important for us to understand specifically some of their properties and why and how we can make better materials themselves. So I'm going to focus mostly on polymer-type biomaterials, and in polymer-type biomaterials, what we're effectively trying to do is mimic what's called the extracellular matrix. This is an agglomeration of proteins which are expressed by cells at the interface, which allow it to communicate with other cells, to form adhesion groups, and to effectively form a tissue in the end. These are typically things like collagen and other proteins like integrin, which form a bilayer or layer which allows cells to adhere. A lot of the properties of these materials are the fact that they're things like they tend to be biologically relevant molecules like that of silk or collagen. made from amino acids. They're soft and wet and full of water. But specifically, what about their thermal properties, and why is that really important for us going forward? So some of the thermal properties that we here at C-Therm can look at and help measure are some of the thermal stability properties, the heat capacity, which can be very important, water content, which is incredibly important for when you're looking at biological implants. The water is part of our body, so we need to know roughly how much water content is in these types of biological polymers. And some of their polymer properties, like glass transition temperatures. Some of the thermal properties as well are important, like thermal transfer properties, insulative properties, and more or less what their in situ thermal properties are. When you have a bulk polymer, their thermal properties are going to be incredibly different than that of a polymer which is swollen and more like that of the extracellular matrix when we implant it into materials or into people. And also what we strive at here is alternative geometries. We don't require a larger or a huge sample. We can have smaller samples which we can do measurements on. So I'm going to break the talk up into two parts, more or less looking at the performance and stability of some of these implants, and what are the importance of what we're looking forward to for doing research, and some of the thermal properties of biopolymers, looking at folding and unfolding of proteins, glass transition temperatures, and whatnot using calorimetry experiments. So first I'm going to start off with thermal conductivity of some of these related biopolymers. So why is thermal management important in biological systems? So a good example of this is looking at the Utah array. A Utah array is used for electrical stimulation in recording in the brain. So right here pictured is a little rodent with a Utah array implanted at the top of his head into the cortex of the brain. What's really important here is that these are electrical components which can heat up during the process of electrical stimulation. So when we stimulate into across one of the pins right here, this will cause an action potential which we can record, but also we're heating up the surrounding tissue and the surrounding material itself. So we need to figure out how we can thermally manage this. So two outcomes of this can be damage to the implanted device if we don't have if we have too large of a heat accumulation inside of the probe, but can also damage the external cells, because localized heating of neural cells of around 2 degrees or more can actually cause permanent damage to terminological tissue, either through the form of forming glial scars in neural tissue, or through death of the material and the actual neurons that you're actually trying to measure from. So some of the applications towards this, what we're looking at is or what is currently being investigated in industry and in academia, is looking at coatings of these neural probes, specifically coating the Utah array with polymer-type materials. Polymer materials are ideal for this because they can mimic the extracellular matrix, minimizing glial scar formation by having a compliant material, which is also highly water-containing, but also at the same time we can transfer and tune the thermal properties by the way that we process the thermal coating or the polymer coating onto the surface of these probes. By tuning these properties of the orientation of polymer chains, or by crystallinity, we can actually tune the the thermal conductivity properties. So here's a list of just common thermal conductivity of some biological or biomedical materials, such as low-density polyethylene, polycarbonate. And you can notice that a lot of these materials are quite thermally insulative compared to that of water, aluminum, which can be used, and nickel as well. So for us to tune some of the properties of these materials, we need to look at how thermal conductivity actually occurs in polymer-type materials. So heat transfer within a polymer occurs through, it's described as the kinetic and transport of energy transformation of phonons in a lattice vibrations across a polymer. And it's given by this nice little formula right here, where thermal conductivity is equal to 1/3 times the volumetric heat capacity, the speed of sound in the material, and the mean free path of phonons. So effectively, if we decrease this side, if we decrease the mean free path of phonons, we'll increase our thermal conductivity. Now, how exactly can we do this? There's a variety of different ways that we can actually affect this and increase thermal conductivity. And one of the ways that we could do this is by increasing crystallinity inside of the polymer material. So with very low crystallinity inside of a polymer material, we get very insulative type properties, whereas if we increase and orient some of these crystalline domains inside the polymer, we get higher thermal conductivity. Additionally, we can look at the orientation of the chains and amorphous domains of polymers themselves. So when you have a random assortment versus a more aligned polymer system, the thermal conductivity can drastically change. We have a lower thermal conductivity in more of a random chain orientation versus when we're more aligned with in one direction for thermal conductivity. So what's really interesting is by aligning some of these materials, we can see that low-density polyethylene can go up to 0.5, high-density can go up to 0.6, but what's really interesting is these polythiophene nanofibers, which were ranging from 0.2 to up to 4.4 watts per meter Kelvin, just due to the directionality of these polythiophene fibers. Additionally, amorphous silk versus more crystalline and more native silk, we can see the thermal conductivity go from 0.04 up to 6.53. And this is really, really interesting when you want to tune some of these thermal properties of coated materials onto brain probes effectively. But what else can we do with these polymer type of materials? One thing that's really important is to look at the heat capacity and the density in this formula. So thermal conductivity is equal to the thermal diffusivity times the density of the material times the heat capacity. So in general, we can affect this. We can affect the thermal conductivity of a polymer by changing density and the heat capacity of the material. So in the general case, when we have a dry polymer right here, which is sodium polyacrylate, versus a wet polymer, when we swell these types of polymers in a biological system, we can effectively lower density in CP and increase its thermal conductivity. So that's exactly what we need to do. This is thermal conductivity of some polymer type materials. Sodium, you can see here at the beginning of the material that we worked with, which was sodium polyacrylate. In its dry state, has a thermal conductivity around 0.5, whereas as you expose water to it, as we swell these type of materials up, we can get an increase of up to 2.3 times the thermal conductivity, which is exactly part of the reason why we need to measure these types of materials in the biological system that we're going to be accessing, because swelling of these polymers can effectively change thermal conductivity. So it's important not to just trust bulk values of these polymers, but to actually go out and measure these thermal properties of these materials themselves. So I'm going to change gears and look towards thermal effusivity. So I'm going to give you a very boring textbook definition of it first, which is thermal effusivity is the measure of a material's ability to change and exchange thermal conductivity with its surroundings. It's given by this formula right here, which is effusivity is equal to the square root of the thermal conductivity times the density and the heat capacity. But here at C-Therm, we like to look at thermal effusivity as a measure of how cool or warm to the touch a material is. So lower effusivity materials are very warm, whereas very high effusivity materials are more cool to touch. And just due to some of our testing of textiles, we can see this range, it can range quite a bit inside of different textiles themselves. So water being up here at 1600, but we have other materials like dress shirts and different cotton types of materials, which range in effusivity. And this is very important when we're looking at burn treatment. So human skin has a rough effusivity of around 500, 600 effusivity units. So when we have a burn that's occurring on a person's skin, we want to be able to cool this burn so we can treat it, pull some of the heat away from the burn itself, so we can try to allow some of the heating or some of the healing to start to occur. And so what we did is we've tested some of these burn badges that you put on burn bandages, which are made from hydrogels. And when you compare it to skin, we notice that the effusivity is quite a bit cooler than that of human skin. So effectively what you're doing in these hydrogel materials is we're cooling the burn. But we don't want to cool it too much. So we have water here around 1600. We want to tune the effusivity so that we're not discomforting the person that's being treated, but we're also effectively cooling their burn itself. So I'm going to move on to some of the calorimetry stuff that we're going to be looking at, and more or less like how we can characterize biomaterials using calorimetry. Now, why is this important? More or less, I'm going to talk to you a bit about thermal stability in these implanted devices. Thermal stability of implanted devices is incredibly important. When we have polymer coatings on these Utah type arrays, or whether we are coating implants for artificial hips, or even in dental implants, the actual stability of these polymer coatings is incredibly important. In the case of the Utah array, we don't want whatever coating that we're going to be putting onto the Utah array and the polymers for it to degrade and leach out into the brain. In the case of dental implants, we don't want you to drink coffee and then the polymer coating on your teeth ends up just degrading and causing toxicology issues, or be it with friction occurring in artificial joints. We don't want polymer coatings or other protein-type coatings to leach out and cause toxicology issues, or for them to degrade and have minimal performance in the case of protein. So a good demonstration of this application is with calorimetry, looking at the stability of this little protein up here, which is beta-lactoglobulin, which we've appended onto microspheres. So what you see here is the thermal stability of just a DSC run of a protein appended onto these little microspheres, and we can see the protein unfolding here at around 80 degrees. Well, it's degrading and coming off. What's important here is that this experimentation was done at pH of around 4, which is the preparation pH for these appending of these beta-lactoglucan proteins. But when we shift to a more biologically relevant pH, around 7, we see a dramatic shift of the stability of this protein down to around 60 or 70 degrees. And we see the apparent instability of these proteins once we even start adding some media proteins in, or just salts as part of tissue culture. So this is part of the reason why it's incredibly important for us to measure biological materials in their native environment or in more cell culture type of conditioning, because we can see dramatic shifts in the thermal stability just due to the inherent switch of a biological from more of a preparatory to a biological pH. So I'm going to talk to you a bit about some of the heat capacity importance for biomedical devices. So just to start you off, heat capacity obviously is the amount of heat required to raise material's temperature from one point to another. given by this formula that I'm sure we've seen in first-year thermodynamics. But more or less what it is it's the amount of heat that's required to raise the amount of energy required to raise the temperature of a material from one point to another. Now, why is that important? When we look at what it's important for in biological systems is in the case of heat fluxes. So in the case of brain probes, where we're applying a heat flux due to electrically implanted devices, we have a quick transient heat source, which is going to cause some type of temperature rise in the implant or in the electronic devices. So in other words, according to this formula right here, the change in temperature is proportional to the heat capacity of the material. So high heat capacity has more of a stabilizing effect on the temperature change. So in the case of water, we have a more stabilizing effect of the temperature change. It's very difficult for it to occur. But in the case of metals, in implanted devices, a very fast change in a heat flux will have a dramatic increase in temperature. And we can tune this by changing some of the thermal properties of the heat capacity itself. So that's exactly what I just explained. Electronics are often firing. Electronics in implanted devices are often firing and reading in a circuit. So more or less in a transient manner, they turn on and off over time. And for this reason, we want to design materials and our biological devices so that we understand the specific heat capacity can stabilize or allow some of the heat to go out into the biological system. How do we measure heat capacity itself? There's two different ways that we can measure it, either using a typical plate-style DSC, where we have the sample compared to a reference and a reference electrode right here. But with different types of material or different types of experimentation, such as using Calvé sensors, which are more of a 3D type DSC, we have the buildup of measuring electrodes in a ring fashion over the sensor. So we have more of a sense of the entire heat capacity because we're surrounding the actual sample with the thermocouples to measure heat transfer. So in the case of biological systems, where we have a very small protein which is folding and unfolding, or very small heat flow in the case of the TG of polymers, we want to look at using these 3D type sensors because they're very important for us to be able to measure small changes in that of proteins or polymers. So measurement of a heat capacity using a standard pan style relies on three experiments to be run. You run a blank type material, so just whatever your sample is without any sample, a reference standard, which is usually sapphire, and your experimentation. So we're running 3 experiments to measure one property, the heat capacity of the material. It's given by this formula right here. But what's an advantage with 3D is that we only have to run 2 experiments. We only have to run the blank versus the experimentation. This is because the heat flow sensor is calibrated at factory, and it's calibrated to be absolutely relevant due to the resistance heater or the Joule effect. So by looking at we're just going to look at some heat capacity values for some standard biomaterials, one of them being gelatin versus collagen. What's important here is that the first run right here is standard crystalline gelatin, and we can see that there's a dependence of heat capacity on temperature. We see a huge spike of the heat capacity compared to its annealed or amorphous polymer or amorphous gelatin. And that's why we need to measure these types of materials. We need to measure them because they can have a change compared through the processing of gelatin. So after we melt, we see that the heat capacity does not change over time, whereas in the first run, we see a huge dependence on temperature for the heat capacity of the material. So with that, I'm just going to offer you some conclusions. One that being that the influence of water on bulk materials is very important for us to measure, and we need to measure the materials that we're implanting into biological systems because they can change from the bulk properties. We need to measure these at the biological relevant conditions, pHs, and temperatures. And understanding thermal management in the case of Utah array is very important for us to not damage any of the external cells which are interfacing with our biological systems. And with that, I'd like to thank you for your attention. And
yes, thank you very much, Dr. Landry, and a great overview of on the application of biomaterials. Really interesting to learn more about where thermal conductivity plays a role. Found the stuff on thermal diffusivity particularly interesting as well. Of course, we've done a ton of work in textiles related to quantifying the performance from a touch perspective, but it was neat to see that kind of perspective taken from bio-based materials. And then the importance of calorimetry in the characterization of these materials. I thought that was really nicely done. C-Therm, we are partnered with C-Therm instrumentation out of France. In our view, C-Therm is the best in the world at calorimetry with their 3D Calvate method that Dr. Landry presented some information on. We have a fully equipped lab here in Canada, and Dr. Landry's group has been providing that on a service basis for some time now. The calorimetry option, full thermal analysis, and of course our core niche in thermal conductivity and related heat transfer characterization. Look, that really brings us towards the conclusion of our webinar, but I wanted to just leave you with a few thoughts, and then we'll open up for a Q&A. So first off, if you're interested in these webinars, we have others scheduled throughout the year. Please let us know if you'd be interested in attending future webinars. And if you have any topics that you would like us to cover in more detail, we're always looking for ideas on new areas of application that we can talk about that where thermal conductivity and some of the related heat transfer properties are of interest. That feedback can be provided through the chat box or on the survey that you will receive following today's webinar. Now, if you're in the audience and you're working in biomaterials and interested in taking a next step with us, there's a few different options. We can schedule a one-on-one call with your group. We can also discuss some options around providing some testing results for your materials, either on a contract basis, or if you're in the process of evaluating investment in a system, we can also look at an option to support that evaluation with some data analysis. So let us know in the chat box if you'd like to receive more information on either of those options. Okay, that said, we will open up for a Q&A. If you're not going to stay on the line for the Q&A session, let me just thank you again for taking the time to join us online today. I know it's a busy time of year as we try to get back into caught up after the holidays. There's always lots to do, and really do recognize the significance of you spending an hour with us online. So thank you very much, everyone. Really appreciate it. My thanks to Dr. Landry. Great job taking us through this material. Okay, we're going to stop the recording and open up the Q&A session.